All right, because we missed class, I wanted to have an opportunity to just go over some stuff with you related to some things that I wanted to cover with you today. So I decided to make this quick video and upload it so that you'd have an opportunity to see what you might have missed since we have homework due in a week. I want to talk about golden section a little bit because I think if you look at everything uh, in this realm, that golden section is probably going to be the hardest thing for you to cover and to look at. It's a little bit confusing. Okay, so let me go through an example and set this up, and we'll look at it from the context of an example. I want to consider the example of f of x is equal to x cubed minus 6x. F of x is equal to x cubed minus 6x. And I want to search within the range between 0 and to 3 for a minimum. I want to minimize f of x. Okay, so I want to find the minimum value of f of x on the range 0 to 3 if f of x is x cubed minus 6x. Okay, now there are lots of different ways we can do that. In fact, I'm going to go over Newton's method here shortly of how to do that. But we're first going to look at golden section. Now, with golden section, the reason why we like golden section is when it's a nasty equation and you don't know how to do the derivatives of it, golden section works just great. Okay, and this one's not nasty. Okay, this one's not nasty. It's fine, no big deal, right? But if it were nasty, golden section would be nice because you don't have to do any derivatives or anything. It's simply a plug and chug type method. Okay, so we're searching in between 0 and 3. So that defines our lower bound, which is going to be 0, and it also defines our upper bound, which is going to be 3. Okay, that's the first thing. We've got our lower bound and upper bound. Now, we've got really three equations that we need to remember for golden section. Of course, no memorization. You'll be provided these equations. The first equation that we're interested in, it defines the variable called d, and d is equal to the square root of 5 minus 1 divided by 2 multiplied by the upper bound minus the lower bound. Okay? What d essentially is it gives us two more points that we're going to sample inside the range between 0 and 3. Okay? So it gives me two more points that we're going to sample inside the range between 0 and 3. So let's calculate d for this example here. The example that we have is d would be equal to square root of 5 minus 1 over 2 times xu 3 minus xl 0. So if I do that real quick here, I get square root of 5 minus 1 divided by 2, which is the golden ratio, multiplied by 3, I get a d that is equal to 1.8541. Okay, now, two other equations I'll give you will identify our lower bound and our lower and upper test points. Okay, x1 is equal to the lower bound plus d, x2 is equal to the upper bound minus d. Okay, so this is simply a plug and chug procedure to calculate x1 and x2. It should not be difficult for you to do. You just take the lower bound, which is 0, and add d to it. So clearly, x1 is going to be 1.8541 because 0 plus 1.8541 is 1.8541. 3 minus 1.8541 will give us x2, which is 1.1459. Okay, that's great. All right. And let me do this. I'm going to have to make myself some space here. My apologies. I'll put those somewhere else. But those formulas, again, are provided to you, your formula sheets, whatever. Let me put them up here on the top so we have them. Let me just rewrite them here real quick. x1 is equal to xl plus d. x2 is equal to xu minus d. One very confusing thing about x1 and x2 is that x1 is typically greater than x2, which seems a little backwards, okay? But whatever. All right, now, here's the last thing you need to do for each step. you now need to calculate the function of x1 and the function at value x2. So what you do is you literally take the value you have for x1, which is 1.8549, okay? And then you calculate the function. Now the function is x cubed minus 6x. So you do x cubed minus 6x, and you plug in for that value, and I get minus 4.751, I guess, all right? And then also for x2, you get 1.1459, and now you plug that into my function x cubed minus 6x, and I get minus 5.371. Okay, now, here is the point of confusion. Most students can do all that. Students can calculate D, that's plug and chug. They can calculate x1 and x2, also plug and chug. And they can plug in x1 into their function, and they can plug in x2 into their function, okay? The problem and the confusion with golden section is not with anything I've already done. The confusion with golden section is the next step right here. So this is where you have to be very, very closely, just lock in with me for this next minute, okay? Lock in, because this is the confusing part. All right, I'm searching for a min, okay? Okay, I'm searching for a min. So I've got two different values of min. I've got this value minus 4.751, and I've got this value minus 5.371. Which one is lower? That's pretty easy. The f of x2 is lower than f of x1, okay? So I make x2 the center of the new range, okay? Now, before you say, what does that mean? Let me show this to you visually. Let me show you the range. Here's where we're searching. We're searching between 0 and all the way over here, 3, right? It's bracketing. Now, what do I have here? Well, I've got x2 over here at 1.1459, and then I got x3 over here at 1.8541, okay? Notice there are 4 different numbers there. 0, 1.1459, 1.8541, and 3, right? 4 different numbers. Now, x2 is right here. That's the center of the new range. So what does that mean? That means the new range goes between whatever is before it and whatever is after it. I've now boxed in red the new range. What have I eliminated in this process? I've eliminated the range between 1.8541 and 3. Okay? Now, the reason why this is confusing is that if it were a max, I would be looking for the max value here, and I would actually be choosing x1. I'm not choosing x1, I'm choosing x2 as the center of the new range because I'm looking for a min, okay? And that's the key thing. I'm looking for a min. So because I'm looking for the minimum value, the x2 value, 1.1459, resulted in a lower function value. So therefore, it's the center of the new range. My new range now, my new XL has not changed. It's still 0. My new XU is 1.8541. Okay? Once you establish those, the rest is plug and chug again. Okay? Plug and chug again. The hard part is that step I just told you about. Because I tell you, a lot of students get so confused by that. Make the low value the center of the new range. Write all 4 numbers out on a number line between 0 and 3. Write all 4 numbers just like I did. And then identify, oh, which one's lower? Oh, it's this one. Well, that's the center of the new range. Okay? Does that help? Does that make it clear? And then we do it again? Should we do it again? Yeah. Maybe we do it again. Okay. Now, let's do it again, since I know students get trouble with this. Now, what's D now? Well, D, you got to still calculate it out. It's going to be square root of 5 minus 1 divided by 2. That gives you the golden ratio. We're going to now multiply that by 1.8541. The new D here is 1.1459. Okay? Now let's do a new x1 and a new x2. x1 is the lower bound plus D. Okay? Well, 0 plus 1.145159, 459 is equal to 1.1459. X2 is the upper bound minus D. Well, the upper bound is now 1.8541 minus D. You should get 0.7082. Okay? Now, you'll notice something here. Notice that X2, my previous X2 value is now my X1 value. Okay, notice that. Okay, notice that my previous X2 value is now my X1 value. That always happens. That always happens. That one of your previous values becomes another previous value. Okay, you always reuse a value. Why is that important? Because now I don't have to retype that function evaluation. What's my function at X1? Well, it's the same thing as what it was before at X2, right? So I don't need to calculate f of X1. I know f of X1 is minus 5.371, right? I know it because I already calculated it before it was f of X2, right? It's the same thing. So that helps. Now, X2 I do have to redo. X2, I have to plug that into the function. And if I plug in X2 into my function, again, x cubed minus 6x, I will get minus 3.894. Okay? All right. So now, let's do this again on a number line. Let's do the number line. Create the number line every time, okay, if you have trouble with this. I'm searching between 0 and 1.8541. My intermediate values are 0.7082 and 1.1459. Okay? And that's my new range between those four values. Okay? Now, which one, X1 or X2, resulted in a lower function value? Well, it looks like X1 did, right? Because my X1 was 1.1459, and it resulted in an f of X1 of minus 5.371, which is lower than the minus 3.894. Okay? So X1 is the center of my new range. That is this value right here. That's the center of my new range. So my new range is between that value and there. Okay? What have I gotten rid of? I've now gotten rid of this early part. Okay? What's my new iteration? My new iteration is going to go between 0.7082 and an upper bound of 1.8541. Okay? That's my new iteration. And then you just keep continuing. You keep going. The only thing you know, by the way, the only thing you know is that the optimal value is somewhere in that range. You know it, and so the range gets smaller, 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 and the only thing you know is that the optimal value is in there. Now, if you have to choose a number within the range, your best bet is to choose halfway in the range. Okay? If I tell you that the optimal value is between 0.7082 and 1.8541, and you have to stop right now, what are you going to guess? Well, you're going to guess halfway. If you have to stop and you have to guess halfway, because the most error you could be is half the range, right? If you guess halfway, the worst you could be is half that range, okay? But if you guessed 0.71, for instance, you say, oh, what if the optimal value is 0.71? It sure could be, right? And if you guess 0.71, but what if you guess 0.71 and it turns out to be 1.83? Well, you're way off, right? So if you guess halfway, you're always the best you can guess, okay? So that's what I suggest. Now, other thing. That's plenty of stuff on golden section. If you want more, take a look at the video. Let me talk about Newton's method. This always gets a little confusing for students, okay? We've been doing this thing called Newton-Raphson, right? And Newton-Raphson was to solve f of x equal to 0, right? Okay, that's what we've been doing, right? Well, now I have this thing called Newton's method. And some students get confused. They go, what are you talking about? Isn't that the same thing as Newton-Raphson? Almost, okay? And here's the deal, right? Newton's method is almost the same thing as Newton-Raphson. The only difference is that Newton's method is trying to solve this problem. The derivative equal to 0. Notice the difference? Newton-Raphson's trying to solve the function equal to 0. That's what we call a roots problem. That's what we've been on. We already did that, right? Newton's method applies the same formula, basically, to solve the derivative equal to 0. Now, why would we want to do that? The reason we want to set the derivative equal to 0 is that for optimization, that's often the problem we want to solve. Okay? So, for instance, let's take a look at this problem that we've already looked at. Okay? Take a look at this problem we already looked at. I want to find the minimum x for f of x, the minimum value, not the minimum x, but the minimum value, let's say, just to be clear, the minimum value of f of x equal to x cubed minus 6x. Okay? I want to find out what is the x star value that minimizes that function. Okay? That's the same thing that we just looked at with golden section. Right? Well, we know from calculus one way to do this is to solve this problem. The derivative, set the derivative equal to 0 and solve for x. So how would we do that? Well, in this case, it's pretty darn easy, right? In this case, I could take that derivative and set it equal to 0. It's super easy, okay? All right? But let's just pretend that it's not so easy, or let's just pretend that we're using Newton's method to do this, okay? How would we do this? Here's what we do with Newton's method. We're going to solve f of x equal to 0. So how do we do that? Well, remember what Newton-Raphson said. Newton-Raphson said this: x of I plus 1 is equal to x of I, right, minus the function at xi divided by the derivative at xi, right? That's what we call Newton-Raphson. And that was to solve f of x equal to 0. So what if we want to solve f prime of x equal to 0? Well, just do this. Just do this. X of I plus 1 is equal to x of I minus f prime of xi divided by f double prime of xi. Just pretend that your function is the derivative function. It's the same thing. You're just pretending that the derivative function is your function. Okay? So fundamentally, it's going to be first derivative divided by second derivative, because the first derivative is the function I'm trying to solve for, the roots problem for. Okay? So it fundamentally looks exactly the same as Newton-Raphson. It's the same thing we've already been doing, except now we're doing it on the first derivative. Okay? So what do? How do we functionally do this? Well, you take this thing here, right? We got this x cubed minus 6x, right? And the first derivative of x cubed minus 6x, that's going to be equal to 3x squared, right, minus 6. Right? And the second derivative is equal to 6x, right? So that's easy. Now, how do we set this up? Well, what I would do, I have to have a guessing value. Let's start with my x of 0. Let's start x of 0 equal to 1. Okay, set x equal, that's my first guess. X0 is equal to 1. So here's what it looks like. My x of I plus 1 is equal to my x of I minus my function first derivative divided by the second derivative. Oops, hold on, this is second derivative. So that's going to be 3x squared minus 6 divided by 6x. You see that? There you go. So now it's plug and chug. Plug and chug. Let's do one just real quick. So my x1 value is equal to my x naught, which is 1, minus, well, what's that? What's 3x squared minus 6 if x is 1? Well, that's going to be 3 minus 6. So 3 minus 6 is going to be minus 3 over 6, right? So that's basically going to be 1 minus 1/2, right? So if you do 1 minus a negative half, right? So that's really going to be like 1 plus a half, so it's going to be 1.5. Right? And then what do? Well, you do it again. You iterate. You iterate, you iterate. You do it again. And then it will converge to not your root anymore. It will converge to the minimum. It's going to converge to either a min or max. Okay? Now, you really don't know which one it converges to. It could give you the wrong value. Okay? That is definitely possible. Okay? But it will converge to either a local min or a local max, or it could diverge. But you don't know for sure. But that's functionally how you do it. So it's the same thing we've already learned. You just apply it on the first derivative instead of the function itself.